We're now going to take the next step in looking at planetary motion. The next step is to write down the Lagrangian and find the equations of motion. We're going to do it in polar coordinates. The Lagrangian always is the difference between the kinetic energy and the potential energy. We're going to do it for a general spherically symmetric potential U of R. So we'll just note here that for Newton's universal law of gravity, we had minus gmm over R. This is certainly a function of R only. We talked about that before. Not phi, not theta. But I'm not going to insert this into the analysis until later. I want to keep the analysis general so that it could also be applied to other potentials other than the gravitational potential. So T, according to concept 8.4, we can write T as 1/2 m r dot squared plus r squared phi dot squared. And then we're going to subtract u, and that's going to be a function of r. And there's our Lagrangian. So the question is what variables it depends on. Remembering that we're in polar coordinates, x, y, r, phi, for the mass m. We actually see r's and phi's in this relationship. I see an r and an r dot and another r over here. I don't see any phi's, but I do see phi dots. And that's going to give us something very special with phi. It's going to lead to a conservation of angular momentum. But L here really is a function of r, r dot, phi, phi dot, and t. Well, not phi, but it seems like it could have depended on phi. So it's almost like we have two generalized coordinates that we have to deal with, and in fact that's the case. So instead of just having a single generalized coordinate, like we did when we studied the Lagrangian formulation, dl by dq minus d by dt of dl by dq dot, we're going to have to apply that equation for each generalized coordinate. So we have two generalized coordinates, which are r and phi. T you don't think about as a coordinate. You just note that t is the independent variable. It's what r depends on and what phi depends on. So we don't count that t is a generalized coordinate. So we're going to have to write two Lagrange's equations, one for each generalized coordinate. Let's do phi first. dl d phi minus d by dt dl by d phi dot equals 0. All right, let's see if we can do the derivatives. dl by d phi. Here's L. Where are the phi's? Well, we already pointed out that there aren't any. So that derivative is 0. Phi is called a cyclic variable. if the derivative of L with respect to a particular generalized coordinate or variable is 0, then phi is called cyclic. And look what happens. So dl by d phi is 0. Well, let's figure out what dl by d phi dot is. That says phi dot right here. Here's L. Where are the phi dots? This doesn't have any phi dots. This doesn't have any phi dots. This does. And we're going to have 1/2 m r squared. The derivative of phi dot squared with respect to phi dot gives me 2 phi dot. And that 2 will kill this 1/2. So we'll end up with m r squared phi dot. So now, having computed these derivatives, dl d phi and dl by d phi dot, I can now insert them into this, we call this the angular Lagrange's equation because it's dealing with the angles. So dl d phi is 0. So that's this term, minus d by dt of dl by d phi dot, which is this bad boy right here. And all of that is supposed to equal 0. Well, amazingly, therefore, d by dt of m r squared phi dot equals 0. All of us can integrate this equation. How do you integrate it? Multiply both sides by dt, and then put an integral sign over both sides, and then you'll have integral of d times the stuff in the parentheses equals 0 plus a constant. Well, the integral of d anything is anything, and that implies that m r squared phi dot is a constant. And we're going to call that the angular momentum. In fact, we don't have to call it that. We already have dealt with it in, I forget which chapter it is, maybe 3-ish. That's the angular momentum, and it's constant. So we proved conservation of angular momentum. So that's amazing, and that is one of the most beautiful aspects of the Lagrangian formulation. If there's something that's going to be conserved, it just pops out. And it's interesting that if a variable is cyclic, namely if the derivative of L with respect to that variable is 0, then there is an associated momentum associated with this variable that is conserved. So cyclic variables have a conserved conjugate, so-called conjugate momentum. All right, that's all that we need to know from the angular Lagrange equation. Let's try for the radial Lagrange equation. Remember, the Lagrangian depended on both the radius and the phi and their derivatives. So dl by dr minus d by dt of dl by dr dot. That's the radial Lagrange equation. Let's see if we can take these derivatives. dl by dr. In fact, I'm going to save a little bit of time and some board space by doing these derivatives in our head and actually sticking them into the differential equation. I need dl by dr first. This term doesn't involve any r's, but this one does. And I need to take the derivative with respect to r. The derivative of r squared with respect to r is 2r. That 2 kills this 1/2. So we end up with m r phi dot squared. Takes care of that term. Then we have a term involving u. It depends on r, and I need to take the derivative of u with respect to r. But u is an ordinate, it doesn't depend on more than r, it only depends on r. So the partial of u with respect to r is just the ordinary derivative of u with respect to r. That takes care of dl by dr. Then we're going to have a minus d by dt of dl by dr dot. Well, where are the r dots in this guy? This doesn't have any, this doesn't have any, but this does. And the derivative of this term with respect to r dot will have 1/2 m times the derivative of r dot squared is 2r dot. And that 2 kills this 1/2, and we end up with m r dot. Simple as that. All right. Now I'm going to rewrite this equation. Let me take this term here and move it to the right-hand side of the equation. So we'll have d by dt of m r dot, but if I take that derivative, m is just a constant, it comes out, and d by dt of r dot is m r double dot. So when I take this term to the right-hand side, I get m r double dot. And then left over on this side, I've got m r phi dot squared minus du by dr. We would like to write this in the following way, and you'll see why this is important only after we do it, and it's not in this concept, it's in a subsequent concept. I would like to rewrite this as minus d by dr of some effective potential. Well, I claim that this effective potential let's see. To do that, I've got to do one more step first. Before taking this step, I just realized that I need to eliminate phi dot from here by using this equation. Let me call this equation 1. Solving equation 1 for phi dot will give me phi dot equals L over mr squared. I think you can see that. mr. Phi dot is going to be that L over mr squared. That's this term here. Minus du by dr. Now, this just this is mr times phi dot squared. So phi dot is L over mr squared. That's this guy here, and I have to square that term. So let's actually see what this looks like when I simplify it a little bit. I'll have m divided by m squared. So I'll have an m in the denominator. I have an L squared in the numerator. M. Then how many r's do I have? I've got one r here in the numerator, and then I've got 4 r's, r squared squared, in the denominator. So that gives me r over r to the 4th, which is 1 over r cubed. And now I'm ready to claim that I can write mr double dot as minus the derivative of u effective. So here's mr double dot. It's equal to this, and that only depends on r. That's a miracle. It's amazing. And I claim that you can write this whole thing in this way as a derivative of an effective potential, with the effective potential being defined as L squared over 2mr squared plus u of r. Let me write that a little more prettily. Let me verify the claim. I claimed for you that I can write mr double dot this way with this u effective. Let's actually take the derivative. We've got minus d by dr of u effective. So substitute this u effective into here and take the derivative with respect to r. What do you get? Well, I have a minus sign, and then I have the derivative of L squared over 2mr squared with respect to r. Well, 1 over r squared is the same as r to the minus 2 power, so its derivative is minus 2 times r to the minus 3 power. But that 2 kills this 2, and the minus sign comes out, and I'm sorry, we had a 2 in the numerator, 2 in the denominator cancel each other, and then the minus sign from the minus 2 cancels this one, and that gives us this term here. And then finally, d by dr minus d by dr of u effective for this term will give this term. So if that was confusing, then just work it out on your own. Take this, substitute it into here, and show that this equals that. So the bottom line, though, is we now have a radial equation, and this looks a whole lot like Newton's second law. It looks like a mass times an acceleration, but it's an acceleration only in the radial direction. There's no angle dependence here. And it's equal to the negative of the derivative of some potential energy. So this looks like a force. The negative derivative, it's like the negative gradient of a potential energy, where this is the potential energy. This will end up giving us a lot of physics down the road. Now, so this is the angular, and this is the radial equation. Now, I'd like to give you a caution that Lagrange's equations are a little bit picky. And you might be inclined to say, well, wait a second. If L is mr squared phi dot, then I can solve for phi dot here. Phi dot is L over mr squared like we did before. And I can substitute that in here for the Lagrangian, and then I don't have any angular dependence at all. Everything depends on r. And then all I have to do is this radial equation, and I've saved myself a lot of work. Problem is you'll get the wrong answer. You will not get this equation. You'll get something different from it. I think there's a factor of 2. I can't remember exactly why. And the reason that you cannot, once you've figured out what's conserved, you cannot substitute them back into the Lagrangian is that the Lagrangian needs to stay in its natural variables that come out of t minus u. You have to be able to vary all those variables independently and take these partial derivatives. You got a dl by d phi, you got a dl by d phi dot, you got a dl by dr and dl by dr dot. You have to be able to take that derivative while holding the others constant. And this one, you got phi dot mixed up with r squared. So you can't legally take that. If you substitute that phi dot into here, then the partial derivatives are messed up. So that is where we hope to find the radial and angular Lagrange's equations. Let me make sure that we have everything. And the answer is yes. Thanks for your attention.